Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. We're here for Integrated Math 3. We're looking at polynomial functions and graphing them, taking inverses of functions, determining whether functions are even and odd, doing function operations such as adding, subtracting, compositions of functions, things like that. Transforming quadratic and cubic functions, or really transforming any functions of the sort, so things like that. And in this power hour, well, in any power hour, my students submit me questions and I respond to and answer them. Now, I only got 6 questions, copied and pasted them in this form right here. We'll go and see what they are right now. We'll see what I can answer. So it's probably not really a power hour, more like a power 10 minutes, if you will. We'll go and see what they have. All right, in graphing polynomial functions, will there ever be the same point for the line to intercept on the graph? I wish I read this first, actually. Yeah, I don't read these beforehand. So point for the line. So for line, I assume they mean a curve. And polynomial. Okay, actually, even further back, let me just back this up just for a second and just say, there were 4 questions, and it must be the first 4. There were 4 questions that were submitted to me a while back, and I didn't end up ever making a video for them because they were, we were still kind of in another unit, even though I started teaching some of the other stuff. So this stuff must be early on when we're talking about, yeah, literally graphing polynomial functions. I just want to give context to what this is to make sense of the question. So graphing polynomial functions, will there ever be the same point for the line? For a line, I assume they do mean a curve. So let me do this. I'm going to pull up a little graph axes, set of axes here, right here. Let's say that we had some graph that's crossing through -5, -1, 2, and that point, whatever that is. And then I do something like that. So we're talking about things like this, right? A graph that can cross through those things, polynomial, blah, blah, blah. So when they say a line, I assume they're talking about this curve right here. When they say, will there ever be the same point for it to intercept on the graph? If you mean crossing through an like an x, like have an x-intercept, cross through the x-axis? Yeah, if you're talking about multiplicities. So, and again, maybe you know this, maybe you know the answer to this question very well because it's a very old question now, but a graph can have a multiplicity of 2 right here. So at -5, it could have a multiplicity of 2. You could have a multiplicity of 3 at -1 and curve through there. You could have a multiplicity of 1 right there and a multiplicity of 1 right there. So yeah, whenever it hits like this -5 right there, that'd be considered to have a multiplicity of 2. The factorization of that is x plus 5 quantity squared. So that -5 appears twice, or you can, substitute -5 in 2 different instances of this thing right here. This right here would be at -1 with a multiplicity of 3, like that. So that would be x plus 1 quantity cubed, things like that. And this is to the first power right here at x equals 2, that's x minus 2. And then over here would be x minus, looks like 6, also the multiplicity of 1. And that could be our function. I don't know if that's answering the question. I honestly don't know what the question's asking, but that's my best guess given the words that were used there. And I'm just going to go ahead and say yes, they can if they have multiplicities in that sort of way. But that's how they feature. Quadratics or any even-powered things would bounce off of it. Looking at the questions, I don't think anyone's asking why that is. And as far as cubics go, we can kind of snake through like that. So I guess I'll just go and state that right now, and I'll leave that because I'm not certain I'm answering that question. All right, the next question asks, how are you? Now, you probably asked this a long time ago, and at the time, I can't tell you how I was doing. I'll call myself a peachy individual, so I'm doing just fine. And how are you doing, in fact? Leave a comment down below and tell me how you're doing, whether you asked me this question or whether you just want to tell me when you're watching the video how you're doing. I'd love to hear it. All right, next question. How do we determine the even and odd part of the graphs? And if you have a negative coefficient at the start, how does that affect your problem? Max. Oh, Max might have submitted this. I have 2 Maxes in my classes, so whether you're one or the other, hi Max. I wasn't sure if you were talking about like a relative max or an absolute max, and something was in that question there. Yeah, so if this is one of those early, I guess these first 4 questions are the early ones, then we're still talking about the polynomial things. So this was before we talked about even and odd functions, and you're just talking about even and odd degree. Let me quickly just state that portion there to clear the air for anyone here. An even function is and let me pull up this graph thing again. An even function is a function that's symmetrical across the y-axis. So something like this would be maybe considered an even function, because if I flip this thing over, pretend like I could flip it over, and it's the same thing out. If I flip this thing over, it's the same thing. An even-powered function is a function with a polynomial of even degree. So x squared, x to the fourth, x to the sixth, whatever. That just has to be the leading term. It doesn't have to be symmetrical with the y-axis right there. So it can be, something like this, whatever it is. That's not symmetrical across the y-axis, but it's still an even function. Even degree polynomials will either start up and finish up. That's my way of saying it. End behavior. They'll end in the same direction, or start down, finish down, something like that. That's totally an even powered function, an even degree function. It's not an even function, though. So what was the question? How do we determine the even and odd part of the graphs? And if you have a negative coefficient. Oh, okay, so the whole question is really about end behavior. So let's just state this here. I'm going to plot some points. I'll do the same ones I did before. -5, -1, 2, and 6. Sure. Now, where do these things cross through? It'll cross through these points or touch these points, whatever, right? There's a chance it can just do something like this, in which case this would have been an even degree function because of that, whatever. But an odd degree function can exist crossing through these points, especially if one of these just had a multiplicity of 2, something like that. If it bounced off that point and it snakes through. Now the difference between this one and the previous one was when this has an even degree, when this has a multiplicity of 2 right here, that makes that, that x plus 5 squared like that. That means that's 2 x's, that's an x squared right there, times an x right here for x plus 1, and an x minus 2 times x, and x minus 6 times x. X squared times x times x times x is x to the 5th. X to the 5th power. That is the leading term of your polynomial, x to the 5th. So the degree of the polynomial is x to the 5th, odd degree. Odd degree has a end behavior, start and finish in different directions here. So regarding the question that's being asked here, which says, how do we determine the even and odd part of the graphs? I'm presenting you a graph first and telling you what it was, but what I want to do instead is talk about, well, if you have an odd degree polynomial, the end behavior is dictated based on the leading coefficient of the polynomial. If the polynomial is positive, then an odd degree polynomial will start down and will finish up somehow. Let's just pretend like that was your graph. It'll start down here and finish up. That's because when you cube really large positive numbers, it becomes really large positive cubed. And when you cube really large negative numbers, it becomes really large negative cubed, like that. If the leading coefficient was negative for a cubic function or any sort of odd degree, then it would start up here and would finish down below. And that's because when you cube a negative number, it becomes negative, but then you take the opposite of it. Negative leading coefficient will flip-flop it. It'll turn it around. And same with positive. Cube a positive is positive, and then flip it over like that. So, we made a table for our notes in one of my classes here, so I could probably do that, but I'm giving the visual to start with. Even degrees start and finish in the same direction, and your most classic case one is like y equals x squared, something like that, the quadratic. When I square something, it turns positive, right? But that's if I have a positive leading coefficient, if my a value, if you will, is positive. If it's negative, what happens is you square the number, it turns positive, and then you multiply it by a negative number, and then it flips over, it turns negative. It goes from here to something like this, right? Suddenly it flips over like that, and that's what you get. So even degree polynomials start and finish in the same direction, whether they're positive or negative. They start and finish in the same direction. Odd degree polynomials start and finish in opposite directions there. And really the best way to answer it for you is if it's a negative leading coefficient, it'll finish downward. This is a negative leading coefficient, so it finishes downward. Odd degree with a negative leading coefficient will finish downward, but odd will go opposite direction of the other guy, and even will go same direction right there. So I don't really know if that answers that there. I mean, it does, but I don't know if that not drawing a table or whatever is fine as well. I just wanted to kind of give all that, and hopefully it made some sense there. And, I didn't do full on examples. All right, how do you find the y-intercept in this new unit? Oh, well, again, this is now old. Maybe you know the answer here. You find the y-intercept in this unit the same way as you do in any unit. Let me just clarify this really briefly. The y-intercept is the value of y when x equals 0. We know visually where the y-intercept is on a graph. It's where it crosses the y-axis. Great. But if you don't have scales on y, if you can't actually see it, we got to figure out how to determine what it is. You can do it without a graph. The y-intercept of any graph is the value of y when x equals 0. So if you have an equation, if you have a polynomial function, you can plug in 0 for x. It's for f of x equals. You can take f of 0, substitute 0 for x. What value do you get out? That's the y-intercept, right? Where you cross on a graph is, where you cross the y-axis on a graph, I should say. Like boom, 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 whatever. That is 0, comma, whatever. I'll call it b, 0, comma, b. That's your y-intercept. It's when x equals 0. I mean, so that's how you do it. If we had a factored form case, let me just make one up. If I had f of x equals x minus 4 times x plus 1 squared times x minus 6, cubed, then you substitute 0 into here, and then you get 0 minus 4, which is negative 4, times 0 plus 1 squared, which is 1. Negative 4 times 1 is negative 4. Times 0 minus 6 cubed, which is negative 216. Okay, I ran into a little bit of a pickle there. Negative 4 times 216 is something, 864. So, but anyway, so, 864, yay, that's my y-intercept. Anyway, so the idea is you substitute 0 into there in factored form. You kind of just ignore the x's right there, but you got to then square the value that's still inside there because that's how math works. If it was in standard form, it's your constant term. So if I had like x to the 4th minus 6x squared plus 2x minus 3, plug in 0 for x, 0, 0, 0, negative 3. That's your y-intercept. F of 0 equals negative 3. It's the constant term. It's not always the last term. What if this said cubed, squared, and x like that? Well, then there is no constant term. That's 0, right? Plus 0 right there. So that would be your y-intercept. So to answer the question, any y-intercept at any time is the value of y when x equals 0. Substitute 0 into your equation, and there it is. If you're looking at factored form, you have to calculate a little. If you're looking at standard form, it's the constant term. And that's it. Okay, 2 more questions. How to tell if a graph is even or odd? Okay, so this sounds like, first of all, this is not one of the original 4 questions, so this might be a very new question here. 12 minutes in, geez, I kind of talk over myself a lot. So this is talking specifically about the even or odd stuff. Now, I kind of just answered this in a previous thing to differentiate odd versus odd degree. My tip of my stylus is a little broken here. How to tell, you asked if a graph is even or odd, so I don't know if you mean on a graph. But on a graph, and I answered this a little bit ago, an even function would be symmetrical across the y-axis here. So that, what that means graphically, that looks terrible here. What that means, and this will not be perfect because I'm not really looking at the actual points, just seeing if my drawing looks kind of good. So don't really look at the numbers themselves, they're probably not right. But here's the idea. Is there symmetry across the y-axis? Is a y value, do we get the same y value for opposite x values? If this is some x and we get this y right here, for the opposite x, do we get the same y out? Does f of x equal f of negative x? Substitute something in. So pretend like this was 5, 3 and negative 5, 3. Right? And it looks like I drew that actually okay. 5, 3, negative 5, 3. That means f of 5 equals 3. F of negative 5 equals 3. Therefore, f of 5 equals f of negative 5. That's how these things work here. Now, when we tried them in equations, right, testing them out, we would not actually substitute an actual number because the problem is you can't prove something by example. Because what if that was true? And what if this was true right here, that f of 3 is negative 2.5 and f of negative 3 is negative 2.5, whatever. What if all those are true, but those were false positives, meaning it doesn't work for all values of x, right? So what we tended to do is we would actually substitute literally negative x into there. We would actually substitute negative x into there and kind of see what would show up. And we would clean it up and see, do we get the exact same expression out for an even function as we would plugging in negative x with, excuse me, let me say that again. Would we get the same thing out plugging in negative x as we would by plugging in x? Which is you end up raising things to even powers and things like that because it negative something squared is positive, x squared, things like that. What was I going to say to this? Oh, and so we got to use variables for something like a proof to justify it, to be absolutely certain. For every x, it has to do with every x, not just for 5 and negative 5 and 3 and negative 3. False positives come in a lot of different forms there, and I know that it can sound a little odd to say that, and we can support it with a graph, right? I think you can look at a graph and determine its symmetry from there. At some point, we're going to have to live with it based on a graph if we don't have the function. But, there can be instances where, like, and I bring this scenario up for different things a lot, but, let's say that you're looking at fire trucks and you say, hey, there's a fire truck, it's red. There's another fire truck, it's red. And all your life growing up, all you've seen were red fire trucks. I can understand why we can make a conjecture, or if someone said draw a fire truck and color it in, whatever. We're all going to conjecture that all fire trucks are red. You know what I mean? You've only seen red fire trucks in your life and blah, 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 blah. So you might make a conjecture and say all fire trucks are red. That makes sense. But that's not true. I mean, all it takes is someone painting another fire truck a different color, but, you know, you can go to Google and type green fire truck, black fire truck, yellow fire truck, blue fire truck. They all exist. Probably gray fire truck and silver fire truck and purple fire truck. Somewhere, you know, they all exist there. But it just takes one. It just takes one. So you can't say, there's a red one, there's a red one, there's a red one, and take 1,000 red ones and still say, see? Therefore, all of them are red. No, it just takes one to dismiss it. Same thing here. You can show me every point in the world and its opposite, and you get the same height. And I know I'm stretching out this answer. But you can give me every point in the world, almost every point in the world, so many points, and say, see, the opposite, and that f5, f of negative 5, same y value. But it just takes one to be different. So what we do is we plug in x and negative x, and we see what happens there. Okay, that's an even function there. An odd function, and I won't spend as long on this at all, but an odd function is symmetrical across the origin. So I tend to do this as a classic case right here. Pretend like that's one. Symmetrical across the origin. That means when you substitute some x, you get some y. When you plug in the opposite x, you get the opposite y. That doesn't mean that y becomes negative. It's just opposite sign. Same with the x. You're switching opposite sign right there. You plug in some x, you get some y. You plug in the opposite x, you get the opposite y. That doesn't look quite as good. Plug in the opposite x, you get the opposite y, right? So it's just that idea right there. So if there was some sort of, f of 6, pretend like that's f of 6 equals 3, and over here was f of negative 6 equals negative 3, or whatever. The f of 4 is negative 2, f of negative 4 is positive 2, things like that. That's the odd function idea. And again, when you substitute it into an equation, the negative x, literally, you should get the exact opposite of your function. And I know some people have some trouble with that one because you're assuming all signs should have to switch. And that's not necessarily true. That would be true for a polynomial without anything factored. But, if you have some sort of fraction thing or a product, you just have to make sure that you have the exact opposite of your original function, which means can you factor a negative out of there and get the exact original in there, as if to say that f of negative x should equal the opposite of f of x. Remember, f of x means y. It means the y value when you plug in negative x versus the opposite of the y value when you plug in x. And that's what we're doing here. Like f of 6 is negative 3, or f of 6 is 3, f of negative 6 is negative 3. Therefore, f of negative 6 is the opposite of f of 6, as an example, not as a justification. All right. So anyway, hopefully that answered that question. I spent way too long answering these things here. I'm trying to really stretch out the power hour. Last question here. If you square or cube the value of b, depending on the function's equation, okay, I know what they're talking about, how does it always give you a? And can you always graph accurately based on that value? Yeah. So the thing that's being asked here is, recently, and this must be a question of recent stuff, recently we've been talking about function transformations. And, can't get too deep into it here, but it's this appearance. Let me actually use b. It takes on this appearance right here. So your function is this f of whatever, f of that. And then we have a transformed g of x based on that, right? G of x is the transformation of f of x such that there might be a parameter a, which represents a vertical stretch factor, b, which represents a horizontal stretch factor, h, a horizontal translation, k, a vertical translation. Those are different parameters that could exist in your graph, or not, right? So we can have g of x equals 2 times f of x. And remember, f of x is some sort of equation, whatever it is. It could just be x squared. It could be x cubed. That's what they're talking about, quadratic, cubic, things like that. And, we have a bunch of those. But this would represent an a value right here. So this might say something like 2x squared, right? If f of x is x squared, then g of x may be 2x squared. A transformation, stretch factor, vertical, stretch factor twice. All right, to answer their question here, they're asking, what about a b value? What if it was 2x squared like that? Now this b value right here, that is a b value of 2, which actually means you horizontally compress your graph by 2, a factor of 1/2. Everything's going to be half shrunk in with x. You're going to divide every x value by 2 to achieve the same y value. The question is, can I always square that thing, cube that thing, like this 2 right here? 2x quantity squared also means 4x squared. Well, This is no longer a b value anymore. They're asking you, does it always become a? Yeah, because right here, as long as you're using the function the way it's supposed to, not all functions can do this, and we haven't run into the ones that you can't, but you square it, you cube it, do things like that. Yeah, this suddenly is a equals 4. And then the question on top of that is, can you always graph accurately based on the value? Yes, these are both the exact same graph. If you graph a quadratic in x squared, y equals 1, 1, 2, 4, 3, 9, and then you horizontally compress it by a factor of 1 half. So you make it 1 half 1, 1, 4, 1 and a half, 9, 2, 16. Could have I just graphed this instead? Yeah, 1, 4, 2, 16. They hit those same points, and the in-betweens that we probably don't graph on the halves, they are the same graph there. So yeah, you can do that. If this was cubed, you would cube the 2, and this would turn into 8x cubed like that. Suddenly a is 8, but the same things still apply. These are actually the same graph there. Now, different kinds of graphs where you probably maybe wouldn't do it, you could do it here. What if this was g of x equals the square root? What if this is square root of x? So square root of 2x here. Would you want to take the square root of 2 and call it the square root of 2 times square root of x? Meaning your a value is the square root of 2. That means you have to vertically stretch something square root of times larger. It's around 1.4 times larger. Are you interested in taking 3 and multiplying it by about 1.4 and 7 and multiplying by about 1.4? Or would you rather take your square root graph, which you may not know how to do? Would you rather take your square root graph and take half, compress it by half in the x direction? Just divide your x values by 2. I think I'd probably rather do the former in that case. It all depends. There are some others that you can't really do it with, that you sort of can, but it's not an a value anymore. When we do logarithms, like log of 2x right here, that would become log of 2 plus log of x, which means suddenly that's no longer an a, because a has to multiply by your function. This suddenly becomes a k value. That's k equals log of 2. And I don't even know what log of 2 is as an actual value. And that's a vertical shift, and I wouldn't want to play with that as a decimal. So I wouldn't want to do it there. If you had something like the sine of 2x right here, I know that there is a double angle identity for sine of x, which turns into 2 times sine of x times cosine of x, which means that your a value is no longer really an a, like 2, because now there's a cosine. I'm not getting into that, but the point is, this doesn't just turn into sine of 2 times sine of x or whatever. There are some that you can't and wouldn't really do it. Polynomials, squaring, cubing, and stuff like that, yeah, totally can. And I'm generally a fan of using the vertical stretch factor more so than the horizontal stretch factor, because it's more commonly shown. It presents itself a lot more commonly generally. And because the inverted principle, I'm fine with it. If it says 1/3, I get that I'm supposed to stretch 3 times more for a b, but some people don't, and that makes it a little bit harder. Okay, I hope that answers your question there, and I hope that answers everybody else's questions. This is Mr. Robinson. Thank you so much for tuning in on the Q&A Power Hour here late on a Saturday night. I'll see you in the next one. Take care.